Thanks for inviting me. It's really special for me to be back in Edinburgh, so great time. It's an exciting conference, and yeah, good to see familiar faces. Yeah, so today I'm going to talk about not so much higher symmetries, which has been most of the week in this collaboration, but more derived symmetries. So that's okay. Called a higher Segal-Sugawara construction, which is a construction in conformal field theory about producing stress tensors for a certain family of conformal field theories. So most generally, a stress tensor is a conserved Noether current for space-time symmetry. And there's a special thing that happens in two-dimensional CFT, which is that this stress tensor enjoys sort of an enhanced symmetry by an infinite dimensional Lie algebra. And this Lie algebra is called the Virasoro algebra. So the Virasoro algebra is a central extension of what's called the Witt algebra. And the Witt algebra is nothing but vector fields on the punctured, if you like, formal disk, algebraic disk. There's various versions of this. And in fact, it's the unique non-trivial central extension of the Witt algebra. And studying representations coming from CFT for this Virasoro algebra are very important. In particular, there's a very important invariant called the central charge, which is telling you how this central term acts. I want to emphasize in 2D CFT, this is a unique notion. There's a unique thing we mean by central charge. It's a very important invariant of a conformal field theory. So the idea for this talk is to generalize this notion to look at the stress tensor in a higher dimensional field theory. There's two sort of ways I could think about generalizing the stress tensor here. The first way is how I motivated sort of generalizing the stress tensor in a conformal field theory. This is, not something new. This has been done in physics for a long, long time, of course. But there's an accident that happens in 2D CFT, which a CFT is very close to being a holomorphic theory. So in particular, CFT always splits in between a holomorphic times an anti-holomorphic field theory. And the sort of stress tensors I'm going to be talking about today are generalizations of a holomorphic in a holomorphic field theory. So higher dimensional stress tensors in a holomorphic field. So I'm going to look at the stress tensor of an n-dimensional holomorphic field theory. And we're going to find that there's also infinite dimensional symmetry enhancement. Importantly, though, the symmetry is inherently derived. And by derived, I mean something just very basic well, at this level, maybe it's very basic. So this is just an ordinary Lie algebra, and it's very important here in the higher dimensional world to work with derived Lie algebras or differentially graded Lie algebras or L infinity algebras, if you like those two.
It's in both positive and negative degrees, or it's in 1/2?
It's only in positive degrees, yeah. So it's totally derived, yeah. Nothing very higher about this.
Positive wait, which
homological degree.
Homological, okay.
And as an example, towards the end, as an example of the Sugawara construction, which is sort of studying then representations for this infinite dimensional Lie algebra here, derived Lie algebra, we'll consider a higher dimensional version. A higher dimensional version of what's called the free boson CFT. Really, it's called the chiral. I'll study just the chiral part of that, which describes very simply the chiral sector of maps from Riemann surface into just a circle. Okay. So that's a nice CFT. This thing splits into chiral and anti-chiral parts, and I'm going to be generalizing the sort of chiral half of that CFT. But for the first part of the talk, I'm just going to be working with some algebra.
the case that all field theories in your talk are going to be CFTs?
No, they're all going to be holomorphic field theories. So what this means is that they depend just on the complex structure of the spacetime. So I'm not generalizing in the direction of conformal. I'm going to be generalizing in another direction, in the direction of complex geometry. There's a similar, maybe I'll just point out that there's a similar sort of derived enhancement of conformal algebras that's been recently studied in the work of Kapranov. These are derived symmetry derived enhancement of the conformal algebra, which, as we probably know by Liouville's theorem, are finite dimensional in higher dimensions. This is a sort of fact about conformal geometry. In fact, there's an infinite dimensional sort of derived enhancement of that thing. I'm not going to talk about that. But these things are closely related once you start to talk about supersymmetry. So my sort of starting point is this result in complex geometry due to Hartog, which says that functions on the punctured n disk are isomorphic to functions on the n disk when n is bigger. So you already see my sort of aim to generalize this Witt algebra is to not look at the punctured one disk, but to look at the punctured n disk. But as we find immediately, this is sort of we're sort of screwed. Like you're not really seeing anything about the puncture if we just look at functions here. Just look at, I mean, here we're looking at vector fields, of course, but it's a similar thing for a function. But the sort of point is that in higher dimensions, of course, this punctured n disk is not affine. So there's higher cohomology. So the thing we should really do is look at the derived sections of the structured sheaf on punctured space. And for most of my talk, actually, I sort of, when I write this, I mean either a formal or an algebraic model for the punctured n disk. Most of my talk will actually be in an analytic category. So I'll sort of replace this by an analytic version of this. There's sort of an analytic model for these derived sections called Dolbeault cohomology. So oftentimes I'll just sort of replace this by the Dolbeault cohomology of the punctured, now the actual punctured n plane, instead of working formal or algebraic disk here. So I'll sort of be agnostic for most of the talk between the discrepancy between these two. So
Analogous or related by analytification?
they're related by analytification. So if I meant algebraic functions here, then there's always an embedding. And in fact, I can choose a model where I can actually write down a concrete embedding for this thing. And going the other way, if I use formal, you know, there's power series expansion, even in a sense. So I can power series expand derived things here to get, you know, derived power series or whatever. And this thing does have higher cohomology. So H0, of course, let me just work with the algebraic thing. Just to be simple, H0 of this, of course, is just polynomial functions and n variables. That's just what I said here. And then there's higher cohomology, and it turns out to only live in a single degree. It's in degree n-1. And there's a nice way to identify this if I'm thinking in terms of, say, Dolbeault cohomology as polynomial differential operators in these n variables. So these are just constant coefficient differential operators applied to a very particular n-1 form, which I'll call the Bochner-Martinelli kernel. And this kernel is a sort of a higher, it's one of the higher versions of the residue, the Cauchy residue. So it satisfies the following properties. So here, this is a 0 n-1 form on the punctured plane, say. And it satisfies the property that it's for any 2n-1 sphere, I can contemplate this integral. So I'm wedging here with the holomorphic volume form that I have on Cn, and this thing is 1. So in other words, the Bochner-Martinelli kernel wedge with the volume form, the holomorphic volume form, is a representing class for the 2n-1 sphere. Is the 2n-1 sphere class. So this is all there is in cohomology.
The formula for that form in n equals 2.
Yeah, so n equals 2. And there should be a number here. But, yeah. Okay. So in dimension 1, by the way, what I meant by the Cauchy kernel, of course, this is just the Cauchy kernel. It's just 1 over. So when I meant here, I'm writing in some complicated way, just taking higher and higher derivatives of the I mean, if you squint, this also holds when n is 1. So it's just a way, what the cohomology is doing is sort of separating out what you're calling sort of positive Laurent modes and negative Laurent modes. It just happens in higher dimension that these are smeared across cohomology. They don't live in the same degree. But if you squint and just, I mean, this formula makes sense even when n is 1. So this was so this was used by Ferrante, Hennion, and Kapranov to look at higher dimensional versions of the Kac-Moody algebra. So I'll just mention that really quickly. So most of my talk, of course, is about the Virasoro, but I just want to point out another very important class of algebras in CFT called Kac-Moody algebras, affine Kac-Moody algebras. And there's a version which is sort of associated with these derived sections here. So the idea is that, you know, instead of looking at G Laurent series, what you do is you look at, so here G is just an ordinary Lie algebra. So this is just a finite dimensional Lie algebra. Say finite dimensional in the usual case. And instead of looking at Laurent, G value Laurent series, I look at G value derived sections. And that's only, of course, part of the story. And for the affine Kac-Moody, we really look at a central extension of this thing. And they find a whole class of central extensions for this object here, and they're parametrized by invariant polynomials G of a particular degree, namely degree n+1. So this defines a central extension of this DG Lie algebra here. And I won't write down the specific formula because I'll maybe save specific formulas for these central extensions in the Virasoro. But I just wanted to point out that this has been used already to generalize another important class of symmetry algebras in CFT to higher complex dimension in the work of I want to try to do the same for now not looking at the derived sections of structure sheaf, but the derived sections of the tangent sheaf. And this is, and again, you know, I may work in an analytic category later on, and I'll just replace this by Dolbeau resolution of the tangent sheaf, the tangent bundle, holomorphic tangent bundle on punctured CN. And again, I'll be sort of agnostic, but this is going to be my definition of higher dimensional wet algebra. So this is like the n-dimensional wet algebra. It's the analog. This is wit 1, and now we have wit n for every n. So my first result is that so in parallel to the work of Ferrante, Hennion, and Kapranov, I want to now characterize central extensions. So that's what I'll say first. So it turns out that any class in the degree 2n plus 2 cohomology of BUN. Defines a central extension. So in other words, there's a map from here to H2 with so in other words, I'm just saying that any universal characteristic class in n dimensions of degree 2n plus 2 defines a central extension of this Witt algebra, this derived Witt algebra. This is some central extension.
Some of these twos the same two.
Sorry, one second. What was that?
Are some of these twos the same two?
Some of these twos. Yeah. I guess. So it's a little, the one thing that's confusing when I start to write down formulas is that it doesn't look at all like I'm going to write something down bilinear. And in fact, I won't write anything down bilinear. But what I mean by, so when I write this, of course, I mean Lie algebra cohomology. This is just cohomology. But when I write down representatives for this, I'll do some examples in a minute. You're going to obviously see I'm not writing down anything which is bilinear. And already you could see here that I also was not going to write anything down bilinear. I had these degree n plus 1 classes.
But maybe Theo's question could be reformulated as, are there other maps with other degrees that also go from something having to do with BU to something having to do
Oh,
with
yeah, like,
Algebra, the 2n plus 3 go to H3.
yes, that's right. Yeah, there's a full, yeah. You can write this down at the cochain level. There's a map. Yeah. So there's some cohomological shifts around. So you should think about this as sort of like a transgression map. I don't want to get into that, but this is some sort of transgression that's going on here. But sort of what saves you is that, when I consider Lie algebra cohomology here, there's actually two gradings around. So there's the usual grading you're thinking about in Lie algebra cohomology by symmetric degree, sort of like this, or anti-symmetric degree. But there's also an internal cohomological grading because I'm working derived. So these are DG Lie algebras, so there's also an internal grading here.
Very well for that, if the transgression now become degree 0.
What's that?
I consider that additional DG grading of your transgression map then become degree 0.
If I shift everything appropriately, yeah. But the shift exactly comes from the sort of, I mean, this Bogner-Marnelli thing now lives in a non-trivial cohomological degree. It's really coming down to this fact here, that integration now carries the residue carries some non-trivial degree. This higher residue does. So you could check if I'm BSing at all. So let's just look at the case n equals 1. Sorry. I told you that there's a unique central extension of the Virasoro, so let's not make sure we contradict anything. And indeed, that's true. I'm looking at H4 of BU1. There's just one thing there. C1 squared. So this C1 squared class is what corresponds to this usual Virasoro extension. I'll remind you sort of the geometry of why that's true in a minute. But at least it checks out. But as we can already see, when n is 2, we're looking at H6 of BU2. And of course, there's two things there. So here's an example. Let me look at just this guy. So I'm going to tell you sort of a shadow of what this map is here. I'm going to tell you exactly what the central extension looks like. So what do I do? I take 3 vector fields. So it's going to be a 3 linear thing. And it factors through this residue, as I said, if you believe me that this is constructed using some integrations and transgression. It still is written as the residue over this. We're in complex dimension 2, so the relevant sphere is a 3 sphere. And it looks like this. So we look at di alpha I. So in this model here, I'm using sort of a Dolbeau model here. So here the alpha I, beta J, and gamma K's are all just like Dolbeau forms on C to the n. So here I'm using triviality of the tangent. I can trivialize the tangent sheaf at least, and I can just write an arbitrary section, even a derived section in this way, where these are just Dolbeau forms. Sorry. That looks like that. And you can sort of see a shadow of the cube of the first Chern class. Indeed, there's 3 traces that appear here. So this is the trace of the Jacobian of this vector field. Really, it's a derived vector field because its coefficients are not functions, but they're Dolbeau forms, but I can nevertheless consider the Jacobian matrix. It's a matrix of differential forms now. So that's the trace of that Jacobian matrix. That's also the trace of the Jacobian matrix. That's also the trace. So you can sort of see why maybe this thing, where this thing's coming from. And then I've also sprinkled in some more derivatives, which I had to in order to integrate. So these are holomorphic derivatives. This is the, just, those two appear there. And now we can start to count degrees. So this thing is clearly 3 linear, but I'm integrating over a 3 manifold. I have 2 differential forms here coming from the de Rham operators, so I need 1 more. So that's why this thing is degree 2. So clearly not a bilinear thing, but nevertheless, it determines in a derived sense a central extension of the Witt algebra, where the central parameter still is in degree 0.
The field theory happen to be conformal as well? Are these related to A and C anomalies?
Yeah, I'll mention a result like that. So I only have a relationship when I have supersymmetry. So there's a relationship between, there's a bijection, there's a linear bijection between these 2 classes in A and C in the case of 4D supersymmetry. So if I have a supersymmetry, if I have a superconformal theory in 4 dimensions, there's a bijective correspondence between these classes, and this passes through the twist, of course. I'll say something more refined about that.
I sort of hope there was something more general, or if you just had it scale invariant. Sorry, what you mentioned is the most natural setup.
Sure, yeah. I think I get what you're going for. Maybe we could talk about that when I bring it up again. So I just wanted to point out a little bit of the geometry, what's going on here. So the central extension, as we know in CFT, is really a shadow of some anomaly. It's a shadow of the Weil anomaly, this conformal anomaly in his conformal field theory. And one way to sort of think about that is to consider the following problem. So to consider so the central charge is the first Chern class of some determinate line bundle on MG. So let me just maybe unpack this sentence. So there's this nice manifold called the universal, there's this nice Riemann surface called the universal Riemann surface over MG. And given any, so sort of even before talking about this, given any CFT, it's, it deserved to think about it as a family of CFTs over the moduli space here. That's sort of what conformal field theory is all about. One way to produce those, though, is to consider to let V be a holomorphic vector bundle on the universal curve. In other words, this is one of these sort of natural vector bundles in geometry. So like the tangent bundle, or structure sheaf is fine too. Trivial bundle, cotangent bundle. These are all natural vector bundles, and I can apply this determinant bundle construction, this equivalent determinant line bundle construction, to such a natural bundle. So I should look at the derived push forward of this vector bundle here. And the sort of CFT associated to this holomorphic vector bundle has an anomaly, which is measured by this first Chern class. And by Grothendieck-Riemann-Roch, this is given by the fiberwise integration of some class. And this class is whatever Todd times CH of V. And I just wanted to argue why these, or one sort of vague geometric argument as to why these classes are appearing. I'm writing this for the, I'm writing MG, but I mean, this could just be the moduli of complex manifolds in any dimension. This problem still makes sense. But here you see that I want first Chern class, that's something in degree 2. The fibers here are dimension 2n. So in order to get something in degree 2, then I needed to start with some universal class, which is of degree 2n plus 2. So this is sort of a heuristic argument as to why these degree 2n plus 2 characteristic classes arise pretty naturally from the point of view of anomalies. Not CFT, but even in higher dimensional complex holomorphic field theory. So by a holomorphic field theory, again, I mean one which sort of exists over the moduli of complex structures.
You were the genus, right? Not the dimension.
Yeah, I was just, by this now, I just mean the moduli of all complex n manifolds now. So I fixed a dimension here. So this is the moduli of n manifolds, which I'm not claiming to construct rigorously. I'm just, giving sort of a heuristic here. But in the case of MG, this is very rigorous. Any question? So maybe just to end this discussion here, the partition function of a holomorphic field theory in dimension n should be naturally thought of as not a function on M, this moduli space, but really as a section of this determinant line bundle. And this anomaly is sort of telling you what sort of twists this line bundle has, like how non-trivial this line bundle is. Cool. So maybe just to leave it as a definition. So given C in H2n plus 2, I get this higher dimensional Virasoro algebra, which is a central extension via this transgression map. So importantly, I don't have a unique one, but I have one which corresponds to characteristic classes. So I want to change gears a bit now and talk a bit about an enhancement of Noether's theorem and an enhancement of these algebras here to factorization algebras. So here's the input data. So the sort of symmetry that I'm going to consider to apply Noether's theorem is not just going to be an ordinary Lie algebra, but it's a richer object, namely, it's going to be a sheaf of Lie algebras, which of course all of the symmetries we've talked about so far do fit into this class. These are not only Lie algebras, they in fact enhance to sheaves of Lie algebras on spacetime. The tangent sheaf for its derived sections, we have the Earlier, we had the structure sheaf and the reference to the Kac-Moody algebra. So this is a sheaf of Lie algebras on spacetime. So it's some sort of local symmetry. And I'm also going to allow for the possibility of an anomaly, which takes the form of a certain cocycle for the sheaf of Lie algebras, which is sufficiently local. So because this is now sort of a local object on spacetime, I can also ask for my cocycle to be local as well. So this is going to be a class which I'll call, so it lives in H1. I'm not going to worry too much about the degrees right now. But anomalies turn out to live in H1, local, and this is the local cohomology. The local sort of Lie algebra cohomology of L. And what do I mean by that? I'll just say it in words. I mean that I don't, these are all functionals or multilinear functionals on L, just like an ordinary Lie algebra cohomology, but I assume they have a very particular form. I assume that they all factor through some Lagrangian density. So these cocycles all look like the integration against some Lagrangian, which makes sense. I need to say something a little stronger than a sheaf here. I need to know that the sheaf is sort of presented in a locally free way, so that makes sense. But let me not worry about that too much. But anyway, this is the sort of like anomaly class, which is associated to a symmetry by such a local Lie algebra. And construction of Costello and William, given this data, constructs a factorization algebra, given this data on spacetime, which I'll write in the following way. It's and this is meant to sort of remind you of another cohomology theory, namely Lie algebra homology, which to me is still a cohomology. That's okay. Where this was Lie algebra, this was similar to Lie algebra cohomology. And indeed, on an open set in spacetime, what this thing assigns is the symmetric algebra. And I should put compactly supported sections shifted down by 1. So just like in the Segal complex. And then I have some differential here, which depends on theta. So this differential is the usual Lie algebra differential for L, just encoding the Lie bracket. And then there's also a twisting term involving this anomaly. Okay. And let me not write it down explicitly. So instead of going into too much detail, I'll just give you some examples of this construction. So there's some family of there's a family of topological examples. So G is just a Lie algebra again, and M is just any manifold. I can look at the following sheaf of Lie algebras, which is G tensored with the de Rham complex on M. And when M is the very nice manifold called the real line, this factorization algebra, so this factorization algebra is always going to be locally constant because I'm just looking at de Rham cohomology. When M is R, this factorization algebra corresponds to an E1 algebra then, and it's exactly the enveloping algebra. Exactly the enveloping algebra of G. This is when M is R. And when M is R to the N, you get a slightly more refined thing called the EN enveloping algebra, constructed by sort of studied in the work of Ben Knudsen. Here's another example, less topological flavor, more in the direction of this work. So I could look at L, which is G tensored the Debye complex on a Riemann surface sigma. That's very similar to the style that we're studying here. And when sigma is the very basic Riemann surface called C. This is now a factorization algebra. It's in fact holomorphic. It only depends on the complex structure. And there's this nice correspondence between holomorphic factorization algebras and vertex algebras. And the vertex algebra here is the Kac-Moody vertex algebra. So it's sort of a pithy way to encode the Kac-Moody vertex algebra. This construction also appeared, of course, in the work of Belenson and Drinfeld. What I'm sort of generalizing in this is this notion of the enveloping chiral algebra in the work of Belenson and Drinfeld, if that means anything to you.
Sorry, I asked basic question. So the previous description of not derived case, what is the relation here? Is it the last example?
This last example?
So in the previous case, you explained the anomaly as a line bundle over the moduli, and this local cohomology class, does it correspond?
So there's no moduli space of surfaces here. This is just about the Kac-Moody algebra, so I fixed a surface. So I'm not studying this moduli of curves here at all. This is just about a fixed curve.
So it's just a complex line.
Yeah. So I mean, the Segal-Sugawara construction, if you like, tells you how to glue this around the moduli space of curves. But maybe I'll leave that for the last section. But here I was just sort of mentioning an example of this factorization algebra.
So what is the relation between H1 log of L and the previous H2?
Oh, thanks. Yeah, sorry, I didn't say what that is. So in this example here, the point is that there's a local cocycle. So theta, so it takes in two forms here. And you look at trace of alpha del beta. That's the cocycle. So that thing's a local cohomology class here, and it defines the level of this Kac-Moody vertex algebra. Yeah, thanks.
About the Belenson and Drinfeld, one more time, I missed.
Oh, so this is just this is sort of I would say it's in a different sort of veil, but it's sort of a generalization of the Belenson and Drinfeld chiral enveloping algebra. I'm just saying that's like special to sort of chiral algebras on curves, where this is sort of more general. It makes sense on in any dimension. It doesn't even need to be like a holomorphic factorization algebra. I'm just saying like that's a special case in the case in this example below. So here's a theorem again of Costello and William, which I'll use in the last part. So first off, any quantum field theory for me is sort of a pseudonym for a factorization algebra. This is where I'm sort of outing myself. It's a small part of a quantum field theory, maybe. It's the part which encodes the observables of a quantum field theory. And this theorem is about symmetries of a quantum field theory. So it's about a structure that you have on this factorization algebra of observables. You have a symmetry. Local observables. Well, with factorization homology, in fact, it knows about all of them. Anyway. Perturbative observables, I should say. Yeah. So if classical theory has a L symmetry. And for example, these L symmetries you can cook up using sort of Noether current methods. So by writing down some explicit Noether currents labeled by L, then there's a map of factorization algebras from this factorization algebra here into the observables.
It is now a universal class. Like,
No, so theta is the anomaly class for this symmetry. So here I'm assuming that I have a classical L symmetry. I'm assuming I'm not saying that I can quantize the symmetry, but what theta is telling you is how projective the symmetry is at the quantum level. So theta is like this sort of anomaly to being a full symmetry. It's just a projective symmetry.
It's something I compute from the,
And it's something you compute from the classical theory, but it's a quantum. It's like a, I mean, in the examples I'll talk about, it's like a one loop sort of effect. It's a, yeah, but it's a quantum effect. It doesn't have to be just one loop. It could be, this could even be like non-perturbative in a sense. So yeah, I interpret this thing as the anomaly. So this lets me make the following ansatz. So let obs be just any factorization algebra. No. It could be the factorization algebra associated with some quantum field theory if you like. But I could now define a sort of holomorphic structure. I don't have a better name for this yet. On obs is a map of factorization algebras. Which I'll maybe call scripty T. This is meant to denote stress tensor from the enveloping algebra of this Dolbeau resolution of say X is my spacetime T. So this is this resolution of holomorphic vector fields that I wrote down before. You can twist this thing by one of those classes C that I was mentioning before. This works not just at the level of algebras, but at the level of factorization algebras. In fact, I'm sort of sweeping that under the rug. But it's a map of this into observables. And all you should be thinking here is that just at the sort of most basic level, if I just look at the sort of linear part of this, this is like some Lie algebraic homology. The linear part of this is compact support. It's just labeling for every holomorphic vector field. I have a current, I have an observable in my theory. So this is, that's how you recover the sort of Noether current, but the sort of theorem of Castello-Guglielm says that this actually, in fact, extends to an entire map of factorization algebras.
I'd be thinking of this C theta as universal enveloping algebra, the gauge group or something like that.
So in the sense that this is like the gauge group. Yeah, exactly. Yeah, that's right. And just let me just point out when n is 1, the complex dimension is 1, this recovers the usual sort of conformal structures of vertex algebra.
so I'm type checking correctly. This is a complex manifold and this is a factorization algebra for like the real topology. Is that right?
I mean, this uses the complex structure on it.
When you said it was a factorization algebra, that was with respect to the like just sort of analytic topology.
Yeah, that's right. Yeah. There should be a version of this in higher dimensional chiral sort of algebra geometric world as well. It just hasn't been developed. Yeah.
In Graham's lectures last week, he explained that the stress tensor is supposed to be like the derivative in the direction of the metric, varying the metric. Is there some way that this is like looking at what happens when you change the complex structure?
Yeah, 100%. So the point is for me, maybe let me just denote a complex structure by del bar. So this is about changing del bar, and we know how to change del bar by a 0,1 form with values in the holomorphic tangent bundle. But that's exactly what the Mark-Cartan elements are in here. So it's exactly encoding this sort of shift symmetry of the del bar operator. In other words, it's telling you how to change complex structures. That's right. So in the thing that happens in CFT, of course, there's an accident between conformal structures and complex structures. I'm sort of just isolating the complex structure part and generalizing that to higher dimensions. Yeah. So there's no metric around in particular, but my sort of data here is a complex structure, but rather than a conformal structure. Yeah.
So just like a historical question, was there in Castello-Guglielm or something, was there a notion of stress tensor for factorization algebras on a Riemannian?
Yeah, totally. That's totally fine.
This is.
You can formulate a version of that as well. Yeah, it's going to involve a different factorization algebra here. There's going to, you look at the, yeah, there's a Lie algebra, of course, controlling deformations of a Riemannian metric in any dimension. And you get maps like this, yeah. Okay, so I wanted to go to my example. By the way, there's many examples of factorization algebras which have these structures here. I'm just going to sort of focus on a very interesting one for me right now. There's not many abstractions to producing a lot of examples of this. I just want to actually fit my talk to the title of the talk. So I'll talk about this example here. So in complex dimension 2n plus 2, I'm going to talk about generalization.
Said and wrote different things.
Complex dimension 2n plus 1. I'm going to talk about generalizations of the chiral boson. Which, in dimension 1, of course, by the chiral boson, I just mean the CFT built from holomorphic maps from a Riemann surface into the circle. That's like one chiral boson. I could do higher rank things too. So this is a sort of a generalization of that conformal field theory, chiral conformal field theory. And it starts its life. We start with a sort of topological field theory defined on smooth manifolds. Dimension, real dimension now, 4n plus 3. And that's the boundary of such a thing. So what is this? This is the TFT of what are called flat 2n gerbs. That's a very fancy name. So I want to point out that when n is 0, all I'm talking about here, when n is 0, all I'm talking about here now are flat line bundles. So I'm just talking about abelian Chern-Simons theory. Defined on a 3 manifold. So just ordinary abelian Chern-Simons theory. So this is a generalization of those that makes sense in this dimension. And I'm only going to talk about the perturbative version, so I'm going to fix the trivial flat n gerb and study deformations of that, where I can be very explicit. So perturbatively, it's a very silly free topological field theory. So it just has a single field called C, which is going to be a 2n plus 1 form on M. And the action is just CDC. So these are, many people call these higher dimensional abelian Chern-Simons theories, but it's not about flat connections anymore, it's about flat gerbs. Because I don't have a connection here, I have a higher degree differential form, which deforms the trivial gerb, 2n gerb. So for the remainder, I'm just going to focus on the first non-trivial case. I'm just going to focus on n as 1 for timing and notation's sake. And I'm going to study boundary conditions for this thing. And there's 2 flavors. I'm going to focus mostly on the first flavor, but I want to mention the second one for historical reason. The first one makes sense in the following geometry, where I take my 7 manifold to be the product of a complex manifold. So this is now a complex threefold with the real line, positive real line. But there's a second one, which is studied by Witten. And his quantization of the M5 brane theory, where M here is taken to be a product of a Lorentzian manifold, a Lorentzian 6 manifold. So there's boundary conditions which are sort of natural to both of these geometries here. I'm going to talk about the first one. I'll maybe remark on the second one in a bit. But I just want to say that the sort of theory that Witten obtains on the boundary here is what he also calls chiral theory. It's chiral because there's no complex structure, but it's chiral because it's a field theory which is non-Lagrangian in the sense that it has a constraint. So it's a theory of a two-form whose three-form curvature is required to be self-dualed. But I'm going to study just the complex version of this. So that's another maybe reason why I'm justifying the chiral boson. So for one, the boundary condition is very, very easy. I'm using the complex structure, of course, and what I require is that C on the boundary, which of course is just X. Well, when I restrict it, it's just going to be a three form. That's my fundamental field. And using the complex geometry, what I can do is I can require this to be a 2,1 form or a 3,0 form. And the key point here is that this thing is a Lagrangian subspace of omega 3. This thing is Lagrangian. So it does indeed label a boundary condition. Maybe I'll just point out, this is the one that's relevant for me. For in Witten's work, I require this to be self-dual, like I said, which is another Lagrangian subspace when I have a Lorentzian structure. Okay. But I'm not gonna pay more attention. And I'll just point out that to formulate this precisely, namely to really not to study this thing classically, but to study the quantization of this boundary condition, I should really work in a formalism adept to that, and I'll work in the Batal and Vilkovitsky formalism, where I have to introduce ghosts and anti-fields in addition to all these fields, etc. So really, I should be studying not a simple Lagrangian, but I should be studying a derived Lagrangian. And that derived Lagrangian in case one is the following thing. So it's simply the complex of closed two forms which have an appropriate shift. Here. So I'm shifting down by 1. You see that in degree 0 here, I indeed have this space. And this thing is Lagrangian inside of the de Rham complex of X shifted down by 3.
The first map here?
Oh, this is del.
Oh, okay, okay.
So that's yeah, it's important. So this is the holomorphic differential. Internal to all of these are del bar, which I never write del bar.
Mhm.
So this is a nice Lagrangian, derived Lagrangian. So by doing this, I almost get a quantum field theory, but I really get, it's more like a relative quantum field theory now. And one way that I like to sort of describe that is that this theory almost has an action functional, except it's a non-local action functional. So I'll just write down a sort of pretend world way of thinking about this. There's a real way of thinking about this, which produces a factorization algebra, nevertheless. But so say 2 describes, or sorry, 1 describes a non-local Q of T with action functional S. So alpha is going to be my field. This is alpha lives in this space. And it looks like this. So this makes sense because, well, at least locally, this is del inverse. I don't, del inverse, that's not really an operator, but I'm resolving closed two forms. So I know locally a closed two form is always exact, so I could choose a primitive. And anyway, you can make sense of this rigorously and produce a factorization algebra. And then at the end, I'll just say, there's a family, there's a holomorphic structure on this thing. So there's a holomorphic structure described by the stress tensor. So this depends again on a vector field, like I said before. And you integrate over X, alpha, contract with that vector field alpha. So if you wanted to look at the fields in degree 0, for example, alpha is like a 2 comma star form. 2 comma star form, that's never something I can integrate. But if I contract with a vector field, I get a 3 comma star form, which does have the chance to be integrated along a threefold. So this is really, this produces for me this holomorphic structure that I referenced before. And in fact, I can deform this thing in a 2-parameter way, which I don't have time to talk about, but it's analogous to how, in the world of the ordinary Segal-Sugawara construction, there's actually a 1-parameter family of conformal structures, which is utilized in representation theory. So there's sort of a shadow of that as well, but I'll stop.